Okay, so we'll look at one more theorem about matrices, and one more until we look at structures formed from them. If the matrix A is invertible, then the transpose of A is invertible, and the inverse of the transpose is the transpose of the inverse. Okay, so proof. We're going to look at components. First, we're going to post multiply the transpose of A by the transpose of the inverse. And we're going to look at the component in row I, column J. This component is the sum of products of the rows of the transpose of A with the columns of the transpose of the inverse of A. So the component in row I, column K of the transpose of A is the same as the component in row K, column I of the matrix A. And the component in row K, column J of the transpose of the inverse is the same as the component in row J, column K of the inverse of A. These are just numbers. We can rearrange them, and so we have A inverse, the component in row J, column K, with the component in row K, column I of the matrix A. This sum of products is simply the component in row J, column I of the product of the inverse of A post multiplied by the matrix A. And so this is the component in row J, column I of the identity, which is identical to the Kronecker delta with indices I or Ji, and this of course is the same as the Kronecker delta with indices Ij. And so the product, when we post multiply the transpose of A by the transpose of the inverse of A, is the identity matrix. So next we need to look at the components. When we multiply, pre-multiply the transpose of A with the transpose of the inverse of A. So again, we look at the components in row I, column J. This is the sum of products of the rows of the transpose of the inverse of A with the columns of the transpose of A. The component in row I, column K of the transpose of the inverse is the same as the component in row K, column I of the inverse, and the component in row K, column J of the transpose of A is the same as the component in row J, column K of the matrix A. Again, these are simply numbers. We can rearrange them. So we have a sum of products, and so this is simply the component in row J, column I of the product of A and A inverse. Once again, this is the component of the identity matrix, row I, column J, which is the same as the Kronecker delta with those indices, and this is the same as Ij. So the components in row I, column J of the product, when we pre-multiply the transpose of A by the transpose of the inverse, is the same as the components in the identity matrix. And so we have that the product, when we pre-multiply the transpose of A by the transpose of the inverse of A, is the identity. And so A transpose post multiplied by the transpose of the inverse is the same as when we pre-multiply the transpose of A by the transpose of the inverse, and this is the identity matrix of that size. And so the transpose of A is invertible, and we have demonstrated that the inverse of the transpose is the transpose of the inverse. All right, so now we'll move into vectors, and we're going to introduce vectors as a special class of matrices. A 1 by n matrix is called a row vector. And an m by 1 matrix is called a column vector. So as row vectors and column vectors are matrices, vector equality, sums, differences, and scalar products of vectors are defined as for matrices. But we have a special situation that arises when we look at the product of two vectors in the language of matrices. So before we look at that, let's compare to a larger size matrix. Let A and B be m by n matrices with real components. Then neither the product AB nor BA are defined. However, we can look at the product of the transpose of A post multiplied by the matrix B, and this is the n by n matrix whose components or whose entries are given by the component in row I, column J, of the product of A transpose B is the sum of products over the index K, ranging from 1 to m, of the product of the rows of the transpose of A with the columns of the matrix B. And if we multiply A with the transpose of B, we post multiply A by the transpose of B. This is the m by n, m by m matrix whose entries are given by the component in row I, column J, of AB transpose is the sum over the index k, ranging from 1 to n, of the rows of the matrix A with the columns of the transpose of B. All right? So now we'll look at the vectors. So let A and B be 1 by n matrices with real entries. So we're looking at row vectors. Then the product AB is not defined. However, A times B transpose is the 1 by 1 matrix whose single entry is given by the sum of the products over the index k, ranging from 1 to n, of the row, which is the matrix A, with the column that is the transpose of B. So in this sum of products, there is a single row of matrix A and a single column for the transpose of B. And so there is a single entry when we perform this product. Notice that when we take the transpose of B, it becomes now a column vector. And so we are multiplying a row by a column. And this is what we have called before an inner product, a product of a row by a column. Now let C and D be m by 1 matrices with real entries. So now we're looking at column vectors. Then once again, the product CD is not defined. However, the transpose of C, post multiplied by the matrix D, is the 1 by 1 matrix, whose single entry is the sum, ranging from k equals 1 to m, of the single row, which is the transpose of the matrix C, with the single column, which is the matrix D. So the interesting thing that arises when we multiply vectors is that the result is always a matrix that has a single entry. And so it is convenient to treat the product of vectors not as a matrix, but rather as a scalar. And in the next lecture, when we look at vectors in a more abstract sense, we will see that the standard inner product is in fact defined to be a scalar that satisfies other properties. Okay, so in the previous example, the vector A was a row vector with real entries. So if we were to list the entries of this vector, there is a single row, and so we could list its entries as A1, 1, A1, 2, and so on, up to A1n. But because there is a single row, it becomes redundant to use two indices. And so instead, we say that we have a vector A whose components are A1, A2, and so on, up to AN. Now, in the context, we would need to make clear that we are speaking of a row vector, and you'll often see, rather than square brackets, either parentheses or angular brackets to enclose the components of a vector. Also, in the last example, the matrix or the column vector C was an m by 1 matrix with real entries, that is, a column vector. And so we could list its entries where there is a single column as C1, 1, C2, 1, and so on, up to CM1. But again, as there is only a single column, it is redundant to use two indices. So instead, we say that we have a vector C, and here again I'll use a lowercase with an arrow above, and list its components as C1, C2, and so on, up to CM. And again, using parentheses rather than square brackets, and using the convention of writing it horizontally versus vertically. Again, in the context, we need to make clear that what type of vector we're speaking of, and in this case, a column vector. Now, these differences are not the only differences between vectors and matrices. In fact, there is a much more compelling reason to treat vectors as objects distinct from matrices, and that is that unlike matrices in general, vectors have a geometric interpretation that correspond to a physical meaning. So in the next lecture, we will look at vectors as mathematical objects distinct from matrices and develop the theory of vectors. And we'll begin to look at vector spaces and the notion of an algebraic extension. So we'll end here for today. I hope you have enjoyed the 5th lecture. Thanks for watching.